Next, we will discuss how to integrate trigonometric functions. From the basic rules of differentiation, we know the general antiderivatives of sine, cosine, secant squared, and the product of tangent and secant. But there are no basic rules of differentiation and integration that would provide us with the formulas for integrating powers of sine and cosine, products of powers of sine and cosine, powers of tangent and secant, and products of powers of tangent and secant. So the goal is to fill in this gap and develop the methods for integrating all functions of such type. But first, we need to develop a few techniques that are frequently used when integrating trigonometric functions. Let's consider the following example. We can recognize the pattern and rearrange the integrand, and then set up the substitution by setting a new variable, let's say t equal to sine of x, and finding the differential of t. Next, we plug everything into the original integral, and notice that we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function sine of x back for t. We will refer to this technique as substitution. Let's do the same example again using an alternative substitution. We can recognize a different pattern and rearrange the integrand, and then set up the substitution by setting a new variable, let's say t equal to cosine of x, and finding the differential of t. Next, we plug everything into the original integral and notice that we have nothing but the function of t left in the integrand. We finish the process by finding the antiderivative and plugging the original function cosine of x back for t. Although the answer doesn't look the same, using the trig identities, it can be easily shown that it differs only by a constant. Let's do the same example again using an alternative method. We can use a double angle identity and rewrite the integrand and then set up the linear substitution by setting a new variable, let's say t equal to 2x, and finding the differentials of t and x. Next, we plug everything into the original integral and notice that we have nothing but the function of t left in the integrand. We finish the process by finding the antiderivative and plugging the original function 2x back for t. Although the answer doesn't look the same, using the trig identities, it can be easily shown that it differs only by a constant. We will refer to this technique as trig identities. Let's do the same example again using another alternative method. We rewrite the integrand and choose u and dv and integrate by parts by differentiating u to find du and integrating dv to find v. We apply the formula and combine the like terms to provide a new integral which is the same as the original integral, so we have created a loop. We introduce I to replace the original integral everywhere it appears. Removing all the intermediate results, we now have the following equation in terms of I. To collect all i's on one side, we add I to both sides, and to isolate I, we divide both sides by 2. And now we can add plus c to the result. We now have the answer to the original problem. We will refer to this technique as loop integrals. Let's do the same example again using the loop integrals approach. We rewrite the integrand and choose u and dv and integrate by parts by differentiating u to find du and integrating dv to find v. We apply the formula and combine the like terms to produce a new integral which is the same as the original integral, so we have created a loop. We introduce I to replace the original integral everywhere it appears. Removing all the intermediate results, we now have the following equation in terms of I. To collect all i's on one side, we add I to both sides, and to isolate y, we divide both sides by 2. And now we can add plus c to the result. We now have the answer to the original problem. We discussed and practiced 3 integration techniques that are frequently used when integrating the trigonometric functions.